Okay, let's look at part B of the first subtopic, ocean acidification. So looking at our understanding for this topic, and the dot points are the really key skills that you need to be able to do. So you need to be able to describe and write equations to show how carbon dioxide lowers the pH of the oceans. You need to be calculate the pH of solutions given the concentrations of hydrogen ions or hydroxide ions and vice versa. And you need to be able to write equations for carbonates reacting in acidic conditions. I actually think nearly all of this is potentially revision from stage 1 chemistry and even right back to year 9 chemistry, probably not year 9 chemistry, year 9 science in particular. So this topic we're looking at is ocean acidification. I've included a link here to a short little video that gives a really good introduction to ocean acidification and the problems with it. The chemistry, don't necessarily completely agree with the way they describe all the chemistry, but it's a pretty good way to just start off with that understanding. So, but we'll explore that in a little bit more detail now. So, just in terms of that revision, I think we need to remember that acids can donate hydrogen ions. So, definition of an acid is it's a substance that can donate hydrogen ions. A base is something that can accept hydrogen ions. Or probably more particularly, and this isn't strictly correct, but for the purposes of what we need to know it works, they produce hydroxide ions when reacted with water. So a base is something that will produce hydroxide ions when it's reacted with water. Obviously the hydroxide ion then combines with a hydrogen ion to form water, so that's how it accepts a hydrogen ion. And if you can remember back to looking at the periodic table last year, hopefully you can remember that non-metal oxides form acids. And because they form acids, that's how they're able to donate hydrogen ions. Just another quick little breakdown. We use this square brackets a lot, and that just means the concentration of. So if we put the hydrogen ion in square bracket, that means concentration of hydrogen ions. Hydroxide ion in square bracket means concentration of hydroxide ions. So just by way of recap, for those of you who had me last year, we would have burnt sulphur, a non-metal, burns with a really pretty blue flame. We then would have, as it burns, forms the sulphur oxides, both sulphur dioxide and sulphur trioxide, but we'll just focus on the sulphur trioxide. And that we would have then reacted with water, and we would have used universal indicator to show that it forms an acid. So that reaction is that sulphur trioxide plus water forms sulfuric acid. H2SO4 is our sulfuric acid. You've probably used that a lot in the lab. Then the reason sulfuric acid is an acid is when you put that in water, it will ionize, so it'll break apart to form ions. So the way we just show that we're putting that in water is we use the AQ. AQ means aqueous or dissolved in water. So just to show that we put that in water, and it will release its 2 hydrogen ions. So that's why it's an acid. It can donate those 2 hydrogen ions, and it will form the conjugate base, which is the sulfate ion. Hopefully that's bringing back some memories. Now, carbon dioxide does a similar thing. Carbon dioxide can react with water, and when it does that, it will form carbonic acid. This is what we know as carbonic acid. Now, that carbonic acid can then react with water. And because it's actually a weaker acid, it's not a strong acid like sulfuric acid. So remember, strong acids donate all of their hydrogens. That's why sulfuric acid donates both. Weak acids don't always donate all of their hydrogen. So the carbonic acid, when it goes in water, can just donate 1 hydrogen and 1 sticks with the carbonate ion, and that is what we call the hydrogen carbonate or the bicarbonate ion, or potentially it also can donate both of its hydrogens, and in that case it forms the two hydrogen ions and a carbonate ion. So, but as I said, carbonic acid is a weaker acid, so most of them stay as the H2CO3s, so most of the hydrogens stick with the carbonates, but a small number are then donated, as opposed to the strong acid sulfuric acid that donates all of its hydrogen ions. So, if we have hydrogen ions, that then means that, well, if we have the presence of hydrogen ions, that then means it's going to be acidic. So if we have presence of hydrogen ions, and we'll explain the mass of this a bit in a sec, that therefore means that it will be acidic. Acids have a pH normally between 0 and or up to 7, which is neutral. So the formation of an acid means that we have a low, it lowers the pH. So pH will be less than 7, I guess we could say. That's in the sort of hand-waving explanation. We'll look at the mass of that relationship between hydrogen ions and pH in the next slide. Okay, so now we're going to look at doing those pH calculations, and then we'll get on to that second dot point down here. So pH is a measure of how acidic or basic a substance is, and it's what we call a logarithmic scale. So basically that means if we have an acid with a pH of 1, that would actually be 10 times stronger than an acid with a pH of 2. And a pH of 1 would be 100 times stronger than a pH of 3. So it uses a logarithmic scale, and I'm hoping at some point, somewhere, you've seen logarithmic scales in your maths. If you haven't, please talk to me and ask about that, and I'll go through that bit in a bit more detail. So pH is equal to minus log, which is, I'll come back to that, minus log the hydrogen ion concentration. So look at a really simple example first. What would be the pH of a solution of 0.001 mole per litre hydrogen ions? So to work that out, we just plug that into the formula. pH would equal minus log concentration of hydrogen ions, which is 0.001. Plug that into our calculator, and we would get an answer of 3. So that would be the pH there. Fairly straightforward. If we want to work out the pH of a base of a hydroxide solution, it gets a little bit more complex. Firstly, what we need to do is work out the pOH, which is equal to minus the log of the hydroxide ion concentration. And then this relationship here tells us the relationship between pH and pOH. So pH plus pOH equals 14. If we just rearrange that, we can see that pH equals 14 minus pOH. The book does show, the Essentials book shows a different way of doing this with multiplication. I think this way is a little bit more simpler and straightforward, but if you prefer an alternative way, that's okay, but I'm going to stick with this method here. So let's do a calculation for pH of a hydroxide. So firstly, we work out pOH, which is equal to minus log to the base 10 concentration of hydroxide, which would be 0.1, and that would be equal to 1. Then pH is equal to 14 minus pOH, so the pH would be equal to 14 minus 1, which would be equal to 13. Just running out of room there in that box. So that's how we work out the pH of a hydroxide solution. We've got to work out the pOH and then do that 14 minus the pOH step. Now, we also need to do the vice versa, if you can remember back to that, what the science understanding stated there. And to do that, we use these two relationships here. The hydrogen ion concentration equals 10 to the minus pH, or the hydroxide ion concentration equals 10 to the minus pOH. So we'll do this first one here where we've got a pH of 4.5 and it wants to know hydrogen ion concentration. So the concentration of hydrogen ions is equal to 10 to the minus 4.5, and I will need to get my calculator out and check that. So that would be equal to 3.2 times 10 to the minus 5. I've used scientific notation there. I am making an assumption that you understand scientific notation. If you're not clear on scientific notation, please sing out and ask, and I'm happy to go through that with you. Finally, let's look at a case where we want to do the hydroxide ion concentration from the pH. So again, we've got to do this sort of first step where we work out the relationship between the pH. The relationship between the pH and the pOH, because the hydroxide ion concentration is equal to 10 to the minus pOH. So we go pOH equals 14 minus the pH, which is 13. So that's equal to 1. And then the concentration of hydroxide ions is equal to 10 to the minus pOH, which is equal to 10 to the minus 1, which is equal to 0.1 moles per litre. I didn't realise when I set that up that they're almost both exactly the same. I hope that doesn't cause confusion, but I think that works. Finally, we just need to talk about why is the ocean becoming more acidic? So having more hydrogen ion concentration going to be a problem. And if you've watched that first video, you've probably worked this out. The shells of lots of coral and shellfish and things that live in the ocean is made of calcium carbonate. And you probably remember back from earlier in your years at school doing reactions between acids and carbonates. You know, right back to the vinegar and bicarb volcano reaction if you did that. And when that happens, we get, probably in earlier years, we would say acid plus carbonate gives you salt plus carbon dioxide plus water. So the carbon dioxide is what made the bubbles. However, in this case, the salt is basically, we end up with a dissolved ion. And in this case, we go from having the solid calcium carbonate shell, we lose that carbonate, and we get these calcium ions dissolving. So basically the shell of these shellfish and corals will dissolve away. So the acid coming from the carbonic acid, or mainly from more CO2 in the ocean, reacts with that calcium carbonate in the shell and forms calcium ions, which then dissolve. So the shell dissolves, and we also get the production of carbon dioxide and water in that reaction. So that is, if you like, the chemistry of how the shells of the crustaceans and coral and things like that that live in the ocean are damaged by the ocean becoming more acidic.